things like for every x real number, there is a y real number. This is the kind of thing that we've done at recitation last week. Such that, if I put a comma, means such that, sometimes I write st, such that x plus y equal 4. Obviously, that's a true statement, right? For any x, there is a y such that x plus y equal 4. The way we know that's true, because we can put our hands on that y. For every x, which one is the y? That's the one that we have to argue about. Which one is this y? How much is it? 4 minus x, right? Now, the only thing we have to make sure here is that 4 minus x is an operation that will produce a real number if x is a real number. And that's true, right? If I subtract a real number from 4, I get a real number. So that y is indeed a real number. See, if I change this slightly, this statement, say for any x in, say, n, there is a y in n set of natural numbers such that x plus y equal 4. Is that true? No. Why is it false? Y would still have to be 4 minus x. Numerically, as a quantity, only that y will work out. The problem is if I take a natural number and I do 4 minus that number, I may not get a natural number, right? For example, if x equals 6, 4 minus 6 will be minus 2, which is not a natural number. This sign means it's not in this set. This sign means y is in this set. So it's like a little circle, like an E but round. Means this element in this set. Everybody knows the set of real numbers, right? Any quantity imaginable plus or minus. Right. So what should I do here? What's the easy change to make this a true statement? If I subtract a natural number out of 4, I don't always get a natural number, but I always get an even more less than that. I always get a real number, but I also always get an integer number, right? So if I change this statement for every x in n, there is a y in z, that is the integers numbers, both positive and negatives, right? Such that x plus y equals 4, that is true. How about if I change this n for z? For any integer, if I do y equal 4 minus x, I get an integer. True or false? True or false? 4 minus an integer is always an integer? Yes. All right. So, the order matters here. That's already something we've done at recitation. If I take one of these statements, say the last one, and I say, how about I reverse it? There is a y in z, so I'm just reversing the order of this quantifier here. For every x, I get x plus y equal 4. True or false? So it's the same statement except I changed the order of the quantifier. There exists a y such that for every x, da da da. True or false?
False, yeah.
So what do I do when I change the order? What's the common sense logic? Like, I mean logic in the way we think, not necessarily in the way we write it formally. What's the difference between these two statements? If I change the order, what did I actually do? Yes.
You made it so it's not that every integer has another integer that'll make it 4. It's that there exists an integer that everything that is added to it will always be 4.
That's correct. It's specific to this statement. I meant in general when I change the order. What do I change? I change the dependence. In here, who depends on who? Y depends on x. So for every x, there is a y that could change when x changes, right? If I put x equals 7, I get a certain y. But if I put x equals 6, I get a different y. And if I put x equals 0, I get a different y. For every x, there is a y. It's a different y for every x. How about on this one? There is a y, and for every x. You could say x depends on y, but for every, it kind of crashes the dependency, because if I say for every, it got to work for everything. So this is a much harder statement, because the y has to be fixed, right? There is a fixed y, so for every x this must happen. But of course, the only x, quantitatively speaking again, the only x for which this will ever happen is who?
4 minus y.
4 minus y, right? In terms of any numbers, any quantities, that to get x plus y equal 4, you gotta have x equal 4 minus 1. So you can see right here, this is a false statement, because it says x has to be 4 minus y is fixed, right? Because it's fixed right here. There is a y, so it's kind of, you get to choose one, but once you choose it, you can't change it. It's nailed. So if this is fixed, 4 minus y, it's also fixed. For every y you pick, once you picked it, 4 minus y, it's a fixed value. So x has to be that value, but this one says x has to be any value. So it cannot possibly be that any value has this property. It's a fixed value, right? So when I change the order which I'm writing, I'm changing the dependency, who depends to who. Ends up with me on this example. This y depends on x, so it's not the same y for every x. This one, y is fixed, it's only one y. So you get to pick it, but it's only one value. Once you picked it, x is pretty much fixed by the statement, but the quantifier says has to work for every x. That's a contradiction. Now, how we negate those things? Suppose I take those statements and I want to write the negation of. So for every x, there is a y such that x plus y equals 4. In more generally speaking, this one, in a general sense, says for every x, there is a y, and there is some predicate, let's call it p of x, y, right? That's a statement. The predicate here is x plus y is equal 4. So predicates take, in this case, two variables, and they produce true or false. This is in general, if I make this predicate x plus y equal 4 true, x plus y is not 4 equal false, that would be the predicate. Sometimes I say p of xy equal true, or sometimes I just say p of xy, because that has a true or false value by itself. Right? Boolean functions like predicates, they produce true or false. So this is a particular case of this statement right here. How do I negate this in general? If I want to write the negation, so if I negate, I want a negation of the general statement, yes?
You'd say that there is an x such that for every y, and then negation of the predicate.
Very good. So if I want to negate this statement, I'll say, how is this false? You always have to have a common, like, underlying intuitive reasoning. There gotta be an x for which it fails, because this one says it's true for every x. So to be false, it's gotta be x for which it fails. So there is an x for which this failed. Now what fails? What fails is there is a y, da. Well, for that to fail, it must fail for every single y in here. So that's where the for every y that comes into play. And of course now, what failed? Some property, some attribute, in this case x plus y equals 4. How does that fail? Well, x plus y is not 4. So of course, if this is a true statement, the negation of it must be a false statement, right? How about this one? How do I negate this one here? I changed the quantifiers a little bit, right? The order was, no, I keep the same order, but I changed the sets. So I'm just going to apply the negation here. It's going to be the same thing. There is an x in n for every y in n, so the negation of it, x plus y equals 4. Not 4. So now, if this is a negation of a false statement, but is this how this goes? This is negation. There's got to be an x for each it fails, but to fail means for every y, I must have not the property. So why is this true, right? It's got to be true. If this one was false and I negated it, that's got to be true. So there is an x, and for every y, I can't get x plus y equal 4. In order to prove this statement true, it's enough to just choose that x, right? There is an x means I get to choose it. I only get to choose it once, because it exists first thing. So which x should I pick here? Yes?
Anything greater than 4, so like
Right.
5?
Same x in here that proves this one false is that x that's going to make this one true, right? So x equals 6. There is no y. For every y, 6 plus y. Every y natural number. X plus y is not going to be 4 simply because y is got to be positive, 0 or higher. So 0 plus is going to be more than 4. So let's do something more general. Let's do one more. What happens if I negate this statement here? For every x, there is a y such that. That's a true statement, right? So if I apply the negation, what do I get? The difference is that, actually, I don't want to do this one. I'm going to do this one here. Because I changed the order, so now we get to see something with a different order of the quantifier. All this example one, for every x there is a y, y is a natural dependency on x, right? That's what it means. For every x there's a y. Y can depend on x. In here, y cannot depend on x. There's a fixed y, and this happens for every x. So how do I negate this thing? Can somebody tell me how do I negate it? Yes.
Could you say that there does not exist a y?
I could say negate the whole thing, of course, but that's not what I mean. Exists a y in z for every x in z, x plus y is equal 4. I mean, what does this mean? How do I translate it into quantifier without negations? That's kind of what I did here. I could say not this thing, but then I can transform it into a quantifier expression. Yes.
Maybe for all y, there is an x such that x plus 4 is not 4, or x plus y is not 4.
Right. So not exists means forever, for all. Not whatever means exists. And then, of course, the property's got to be negated. I know it makes total sense when somebody says it, but you got to be fluent in those things, you know, because sometimes you don't think in terms of very simple concepts like x, an integer, x plus y equal 4. Sometimes you have a complicated proof, and you have to be able to see what's that statement that I'm trying to negate right now. Okay, so there are a bunch of rules here that this page here is posted on the website, so you can check them all. Yes.
Okay, so one thing, so when you have there exists as the first statement, if you want to prove that's true or false, well, you can, if you want to prove it's false, you can provide a counterexample. But if your first statement is for all,
the counterexample is for statements that start with for all.
okay.
For all, if a statement starts for all x, something happens. To prove it false, all I need is to show an x that just fails it.
Okay, and then.
But then what happens when the statement starts with there exists a y? How do I prove this one false? In here, if I pick a y for which it happens, that's actually I'm proving it true, right? It says there is a y and something happens with it. So if I pick such a y and I show it happens, that just proves the property. How do I prove this is not true?
You have to show that all of the y's have some such x where the property is not true.
Right. So I need to show this. Right. That's the negation of it. For every y you choose, there is some x that fails it. So that means now the negation of it is true. So the original property is false. Okay. So there's some examples that you should go through. Last time we talked about sequence limits, remember? The last 20 minutes or so had to do with I have an infinite sequence, A1, A2, A3, like 1, 2, 3, or 1.5, 2.5, 3.5, some infinite sequence. And we said when there is a limit. There is a limit when that sequence kind of gets closer and closer and closer to that particular limit value and doesn't get out of that being closer. Once it gets close, it never gets far away. Ends up remembers that. I debated over the weekend whether that should be an optional kind of material or required reading, so I put it in the optional category because I don't know you that well yet, but we'll see. So now I want to extend that property to something you must have seen in high school, which is what's the limit of a function? So function limit, I mean in a point. And the way you've seen this, you probably call it continuity. That has to do with when a function is continuous. So I have a function, is defined on, say, real values with, real values. It takes arguments, real numbers, and processes real numbers. You can think of it as f of x is like 2x squared minus x plus 1. It's the real function. This one in particular being a polynomial, it's an extremely nice function. It's differentials, all degrees, and so on and so forth. Clearly that's continuous. How many people heard of continuity, right? And continuity means like if you plot the function, you get a continuous line, right? Anybody heard of a definition of continuity? So what actually it means? Yes.
You have to have the limit at a point, at every point exists.
So at every point, so we say, let's pick an a real number. That a is in this arc, is in the argument set, right? We say that when x goes to a, like when x gets closer and closer to a, right? The limit of f of x is some number b. So there is, for every a, there is a b. Is that the correct order, or is it exists a b for every a? So what I'm saying here, if this is the graph of the function, this R set here is the argument. This is the argument, right? And this is R is the value. So this is my function. In every point x, it has a value which is f of x, right here. Right? For every x, there is a function value f of x for it. And what I was saying, if you pick a value a, when x gets close to that a, there is some value that the function must convert to. Convert to that value that's going to be, in this case, it's going to be f of a in that point. So then I wrote it formally that says for any number a on the argument set, there is some b. B in this case, it's actually f of a. But that's not true for all functions. This is true for very nice functions. Such that when x goes to a, when this value gets closer to a, it might go from this side too. Or whatever, when it gets closer and closer to this, the function must be closer and closer to this value here. So I could apply the sequence to make this very formal. Any particular sequence of x's that go to a, it could be jumping around, it could be at certain space, produces a sequence of values, if you apply f to it, that converges to this value f of a. So does the order matter here? If I reverse those things, if I say there is a b, I write it the same thing, but say there is a b, and for real number, and for any a real number, limit when x goes to a of f of x is b. Is that the same statement, or is it a different statement? It's a different statement. Why? In this case, b depends on a. For every a you pick, there is a particular b value, that's the function applying to that point. So if you change the a, b will change too. In here, B does not depend on A. There is a global B that's the limit of everything. That's false. So here's how I can write that a little bit more formal. I want you guys to think about this. I'm going to say there is a B, because these definitions are not rigorous, because they still imply something with limits, right? It's kind of a circular definition. I'm trying to define a limit, but I'm defining in terms of lim, arrow, like I can't use that because that's what I'm trying to define here. So now how do we define that formally, mathematically? There is a B, so for every A, there is a B, and for every epsilon, there is a delta, such that if x gets close to A, then f of x gets close to B. So now I have 4 quantifiers. It says, you pick a number A, here's A. Let's redraw this plot. I got an A. There is a B. In this simple case, polynomial function, a very nice function, we know who, by the way, continuity simply states that if this is the case, f of A has to be, if there is a limit in a point A and that limit is B, then f of A has to be B. The function is continuous if the point with which it has a limit, the value of the function in that point is the limit. Otherwise, it means it jumps around, it's not differentiable in that point. So what this one's saying for simple functions like this, nice functions, there is a value here that's B, that's f of A. And this is the gap. If you remember from last lecture, there was a gap that controls how the sequence enters the gap. At some point, the sequence will enter the gap. This one saying this epsilon is around B. It says anywhere you pick a gap around B, say this gap from here to here, around B, that is from B plus epsilon to B minus epsilon. It's an interval around B. Right? For every interval around B, what does it say? There is an interval around A. So here's an interval around A. That is A minus delta to A plus delta. And what does it say in here? If X is in the gap or interval A minus delta to A plus delta, then f of x is in the gap B minus epsilon to B plus epsilon. Then is the implication, right? So what is it saying? Saying anywhere somebody chooses an interval around B, as small as they want, maybe they choose a very small one, there is an interval around A, so that all the values in here, when you apply the function, all these values go in that interval. So in other words, there is some small interval around A, so that all the value f of x go in that interval that somebody chooses around B. So the order of quantifiers here is critical. For every A, there is a B, that's the limit, such that any points around B can be described as a function applied to some interval around A, my function. I would suggest, okay, I'm going to keep this as optional for now. This is essential on the transition for how do we understand, say, discrete math and quantifiers and logic. How does that apply to calculus? I know you've done calculus, but probably not in a rigorous way. You've done formulas and you've learned how to differentiate functions, and so on and so forth. But to do rigorous calculus, you have to be able to build a foundation for how everything works with functions. And this, it may not hit you very early. Like maybe when you talk about, basic computer science. The first 2 years is not. But sooner or later, there will be applications of computer science, like topology and machine learning and AI, when you have to have a good control over what's differentiable and what's not, and why. So that's kind of a fancier example that describes continuity of a function. Continuity is a prerequisite for being differentiable, right? There are examples when continuous functions are not differentiables, but backwards, if you want a differential function, you have to have continuity for it. So let me try another example of quantifiers, unrelated to this. For every, I'm gonna write it here maybe better. For every, maybe you know this one. Red triangle, there is a green circle directly on its left. Sounds familiar? Well, so first of all, sometimes when people write a statement, existential statement like that, you gotta kind of bound yourself to the universe where this happens. What are you talking about? What do you mean triangles and circles? Like in this room, in my house, anywhere on the planet, anywhere in the universe, on that piece of paper? Is that about homework 2? Like, what do you mean for every red triangle? Like every possible red triangle anywhere in this world? Like, okay, well, anybody can draw a triangle anywhere in the thin air, right? Here it is, I call it red. But you can say, no, it's not, because I don't see red, right? So, okay, if I get a red pen, I draw the triangle, then it's red, right? So I think you have to bound yourself to the universe that this is meant to be. In here, that's why we specify the sets. Once we say natural numbers, that's the universe. It's a set of natural numbers. But let's say we got a picture like in homework 2, and we're talking about that picture. How do I write this with quantifiers? I clearly need quantifiers, but I also need predicates, right? So for every means what? A upside down, right? For every, say X, let's call this X. X. Now I need a predicate, or 2 predicates. How do I say that? I'm going to write the predicate now and define it later because it's easier for me to think that way. If I have to break myself for every single thing, I'm never going to finish. So I'm going to say red. That's a predicate. Red of X, right? And then triangle of X. That's any red triangle. I don't need to put equal true because those are Boolean functions. If I state them here, that means they are true. There is. How do I translate there is? There exists. I could put, so I'm going to put a comma and say there exists a y. Or I'm going to ask later if I could put an implication instead of the comma. So the same exact statement, can I just put an implication? Let's see. So I'm going to put a comma for now. There exists a y. Y has to be a green circle. So how do I write that? Green of y, circle of y, and how do I say on its left? I need another predicate that takes 2 variables, right? Who's left of who? But be careful of those things because you can think here one way and then later on you think the other way. So left of, let's say y is on the left of x, something like that. Now we have to write down who this thing is, right? So red of x is who? Is true if x is red, and false if not. It's a predicate. How about left yx? Who's that? True if object y is on the left of x. False if not. So I'm defining Boolean functions which says true, false. So I wrote this with commas, right? For every x, red of x, triangle of x, there is a y, green of y, all commas in there. Is that correct? To put those commas like that? Yes.
Could you use like an and or implication symbol depending on?
Right. Maybe that would be better to say for every x, comma, red of x and triangle of x. Now I do what? Implication. There is a y and green of y. And or I can put a comma here, maybe better. Green of y and circle y and left of yx. And so this is a little bit of formalism. Most people who write this statement with commas will mean the right thing, and most people who read the statement with commas will read the right thing. But this is better, it's less confusing with and signs.
Also, for after like for every x and after there is a y, can you put like the set symbol? Say that there for every x in the set of red.
Right. If x in object set.
Yes.
Right. And y is in object set. That's what I said initially. You gotta bound yourself to some universe. Are we talking about the objects in homework 2? Are we talking about objects in this room? Are we talking about objects, on the street? Or when we say you have to define what you mean for every x. It's too philosophical to say any x whatsoever. You have to be more exact. You mean in a certain set. Yes. How do I negate this? So I don't know if that's true. Whether for every, I'm not worried about true or false. It might be true for the picture, for a particular picture in homework 2, where there is indeed for every red triangle a green circle on its side. And it might not be true for a different. If I draw now a different paper, a different set of triangles and circles, in that set may not be true anymore, right? It depends on what the picture is. Whoever drew this, I can't see the objects because they printed badly, so I can't tell you if it's true or false. But what if we negate it? What does that mean? How do I say this negate? So, yes.
The premise is true and
So how do I write it?
So it would be this.
So negation. There is an x. And how about this part? Is that like this particular property that's in the premise? Is it true or false? Do I negate this one?
No.
This still has to be true, right? I'm trying to show that for every x with this property, something happens. I'm finding an x with this property for which that doesn't happen. That's how I negate it, right? So for every x, there is an x that has the red x and the triangle. So I want to put my hands on a counterexample. One of the stuff that is supposed to have the property, but it doesn't. Then what? Do I still have an implication? Or not? I keep this implication sign, or what do I do with it? So before we continue, let's think about when I say A implies B, remember that's equivalent to? Same as?
Not A.
Not A or B. So what happens if I negate the thing? Negate A imply B is the same as negate not A for B, which is who? If I apply the rule for A and so A is who again? Premise is true and conclusion is? So in order to negate an implication, I need to say a true premise and a false conclusion. And that's how I negate an implication. This is definitely an implication here. It has a premise and it has a conclusion. So how do I now look in here and say, I want the premise and premise true, conclusion false? That's the premise being true. I found an example with the premise being true. And now this implication becomes a and. Now how do I say the conclusion is false? So what does this become? For all y objects, how do I negate this? This has to have three properties. It's a property that needs to be negated. It's a done and done and done. When is this not true? Yes. One of them has to be false, right? If it's like that, and like that, and like that, for this to be false, one of the three has to be false, right? Because it's an and. So how do I say that? Not green of y, or not circle of y, or not left of yx. Now this has to be a parenthesis to not confuse that n with these guys. So again, I found an x in my premise that satisfies the premise such that for any y you pick, the conclusion fails. Fail in here because it's an end of three things. I have to fail one of them. But that depends on really what is written in the conclusion. Because when I negate the statements, I apply the negation rules. Okay. I have a few examples that I want to go quickly over them. You guys gonna you know, you can shout it loud, and then you can take them home if you like it. So here's a bunch of examples in English. Every student at NEU is at least 18 years old. How do I do this with quantifiers? How do I write this? Somebody. Yes.
For all students in set.
I can't say for all students. For all
for
X
all student in set of students.
students at NEU. So this could be done in two ways. I can define a set that the students have NEU, or I can define a set that's all students in the world, but then I need a predicate, right?
Yeah.
So let's see it one way. For all XC students, what?
Find a predicate that says you can.
Age. Is this I could write this as an age of X. It's at least 18. Is that the Boolean predicate if I write it this way? No. What is age of X here? That's a regular function that produces what value? It doesn't produce true or false. It produces for each person what? A number, which is the age, right? How about I write for every X in the student set, that means all the students in the world, if any U of X, that will be a predicate that that student is at any U, right? Then age, if I define age of X and 18 is true. So in here, age is a function defined on students with values in the natural number. In here it's just a predicate. It says true when x is at least 18 and false when it's not, right? So this will be true if age is at least 18 and false if it's not. So that's a Boolean predicate, and this is also a Boolean predicate. A student is at NEU or not. And I need a set that's the set of all students in the world. How do I negate this? If I want to say the negation of the statement.
There exists a student at NEU.
Let's do the first one. It's easier. Such that the age of the student is
Less than.
the negation of at least 18 is strictly smaller than 18. Okay, so I did that one, but I want to give you a bunch of examples to think about. There is an NBA player who makes at least 20 million a year. It's a statement that you get to make, you should write the statement with quantifiers and logic and then negate it. It's an easy one. How about there are at least 2 NBA teams with at least 2 players each. Making at least 20 million a year. That's not easy. There are at least 2 teams in NBA, each having at least 2 players, making at least 20 million. So that would be a nice exam question. Let's see who understood quantifiers and predicates. And then you get to negate that one. Here's another one. I know someone who never experienced moments of doubt. In their whole life. I'm just I'm half joking here. I'm saying if somebody writes something so way into the philosophy, how do you make this like a quantifying statement? I know someone who never experienced moments of doubt. The trick to this one is to see it as a negative statement, as a negated statement. To not write this statement, but write the negation of it. And say, okay, this is the negation of the following statement, and then that one make it into the quantifier, and then negate it to get this one. Yes?
Why would that matter if I define my predicate correctly? I don't know if I do negation or negation.
Sure. I'm just saying philosophy has a way to play with your head. If that's easier for you, I think most people will find it that if you negate this statement, can anybody give it a try? What the negation of this statement is? Everyone experiences a moment of doubt. I think that's easier to write with quantifiers and then negate it. Here's a fun one. In USA, someone steals a car every 15 seconds. I don't think that's true, but I honestly, I got this from a website, so maybe that's true. I don't know what's the rate of stealing cars in the United States. The trick with this statement is this someone the same person that steals a car every 15 seconds? Is that there exists a person? such that every 15 seconds he steals a car or she. So is it starting with an exist statement? There exists a person who steals a car every 15 seconds? Is that a meaning of this statement?
It's for all cars in the US, one gets stolen.
No, it's not for all cars. It's for all what? So first of all, we've established that the someone is a person and it exists, but it's not the beginning of the statement, right? Because once you fix that person has to steal all the cars. Hands up with me on that one. So we don't start this statement with there is a person. We start with
For all time intervals such that the intervals succeeds that.
for all time intervals, all t, which are 15 seconds time intervals. That's the first for all, for any interval of 15 seconds. And then we have what? There is a person, could be a different person every 15 seconds, right? And there's also a car. All right. Let's see what else we have. Everyone has a drink at every party. Try that. How do you negate this statement? Everyone saw a movie at the party. I want to point out the fundamental difference between those two statements. Did you get to write down the quantifiers and negate them? You'll do that at home. When I say everyone saw a movie at the party, do I mean the same movie for everybody?
Not necessarily.
If I just say that statement, everyone saw the movie at the party. So the movie. How about that?
Oh, yeah. Yeah.
But if I say everyone has a drink, do I mean everyone has the same drink? So you got to be careful a little bit. There's a difference between the movie and the drink at these parties. Which quantifiers go first? It matters whether there is a drink, everyone has it, or there is a movie, everyone has it, or for every person, there is a drink, and so on and so forth. Okay, so enough with this. I think we have enough quantifiers. I know the homework is due today, but if you feel like uneasy about the order of quantifiers and negations, you have to practice with examples like this. The best way, until you get very fluent, is to always write the English statement. Whatever the problem's about, sets, numbers, plums, students, parties, drinks, doesn't matter. When you're not sure, even when you practice the things, you have to write the English statement. Okay? So I think we finally ready to move on from chapter 1. It was a fun chapter, right? And we get to do other things. That is, we have to start sets and counting. Do I still have this here? Yes. I want to point out something. Counting is hard. It's really hard. Most people, as in a huge majority of people, 99.9% of the people have a very hard time counting things. I don't know if you noticed that. You may be part of that 1% or 0.1% that does it well and easy, or you may think you do it well and easy. We'll see. But most people have a really hard time with counting. The good thing about that, if there is such a good thing, is that people realize that. Most people I've met in my life who have a hard time with counting, they know they have a hard time with counting. They know, oh my God, that's counting. I don't know how to do it. But people also have a hard time with sets. The difference is, everybody thinks sets are very easy. Yet they're equally difficult. In fact, one of our purposes in this chapter is to show that counting and sets are pretty much the same thing. So you ask somebody who's not a mathematician, give you a sets problem. Would you prefer a sets problem or a counting problem? They're always going to choose a sets problem, thinking that's easier. So as a moral thing, people realize usually counting is difficult. When they see a counting problem, they know they have to climb a mountain there. But when you see sets problems, Sometimes, you know, how hard can they be? And so we're gonna start with a few things about sets that you already know. We're gonna go fast through that. And then we'll see some more interesting things. So everybody knows n, 0, 1, 2, 3, so on and so forth. Everybody knows z, 0, 1, minus 1, 2, minus 2, 3, minus 3. So but these are infinite sets. And then I think most of you have seen Q, which is things like fractions, right? 1/2, minus 1/2, 1/3, minus 1/3, so on and so forth. Here's an immediate problem with sets. If I enumerate n this way, and I put dot, 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 everybody knows what's the next value? What is it? 4. Easy, right? How about in here? 2 minus 2, 3 minus 3. The next one is 4 minus 4, 5 minus 5. Easy, right? How about in here? Can we enumerate all the rational numbers? Like, what's the next value? Huh? 1/4? But if I keep doing this, I only have the one numerators equal 1. Would I ever get to 3 divided by 5 if I keep enumerating things that way? No. So here's the problem, right? Actually, I'm asking two questions here. One is, can we define those sets in a way that's more like general? Instead of enumerating the values, can I actually define it as here's all the values or all the numbers with a certain property, right? And then I'm asking also different questions. Is there a way to enumerate Q, the set of rational numbers? If I really put my mind at it, can I establish some sort of order of the elements that will include all the rationals? But let's answer the first question first, which is, if I am to write Z as a property, as opposed to enumeration, if I am to write this, I'm going to say all x's such that, this is called such that. It's funny how when I write such that in here, it's S dot D dot. But when I write sets, it's this bar. If you don't like the bar, you can just write S dot D dot. Fine. How can I write this as a property as opposed to as a sequence of values? I would say x has to be either a natural number, or, if you don't like or, you can put a logical or what? Because clearly it's not only the natural numbers. What do I need to add here? Either x is natural or minus x is natural. Is that the same set? If I say here's an enumeration of z in an intuitive way. By intuitive way, I mean everyone will find it obvious what's the next value. 4 minus 4, 5 minus 5. An enumeration has to have this obviousness to it. If you enumerate CQ, it's not obvious at all who's next. Yes?
You can't say though that x is a negative natural number.
I'm not saying x is negative. I'm saying minus
Yeah.
x is a natural number.
That's what I mean. But you can't flip the minus to the other side, right?
So put it on here, minus n.
Yeah.
What he's saying, can you write x belongs to minus n? We can if we define minus n, right? Who would be minus n? 0, minus 1, minus 2, up to minus 3, so on and so forth. Is that a well-defined set with enumeration? Yeah. So I could say x is in minus n. If I define minus n, what it means. If I define my set, I could say that. But most importantly, is this the same as this? Like, how do I check the same? Is there any element here that's not on this, that doesn't satisfy this property? Is there any element in here that's not in here, right? So if I find one element that's in one side but not on the other side, That means the sets are not the same. For two sets to be the same, they have to have exactly the same elements. So I think you guys should take a moment to see that everyone here is either in N or minus it is in N. And if I define it this way, I get this set. How about in Q? Can I write a property like this? Like, how do I write Q with a property instead of trying to enumerate all the rational numbers? Yes.
All elements can be expressed like A over B, where A, B belong to
A in,
Z, B, and Z.
so that it's such that the property. B in Z. Is that it? Or what did you say? Let's let him finish.
That's what I said.
Okay, is that correct? Somebody else, please. Is that, if I take any A in Z and B in Z, do I get a rational number? Yes. B cannot be 0. Sometimes people put a star. When you see a star, usually it means not excluding 0 or the neutral element. You gotta make sure though that you understand. Because some professors are really sneaky. They put a star, they imply something else, and then you say, oh, that's excluding 0, but it's not. It means who knows what. Right? So you gotta make sure when you see these stars, crosses, pluses, you say, okay, whoops, what is this? I wanna make sure I understand what the star is. Usually star means not 0. Everybody's convinced that if I pick an integer and another integer, that's not 0, and if I do the ratio, I get the rational number. But any rational numbers, can I write it that way? Is it the same exact set, or one of them has some elements that are not in the other one?
I'm not sure if this is part of the set, but like, would 0 be one of the exceptions?
That's right. Is 0 here in the Q?
No.
Yeah.
Is it?
Q, the rational numbers, contain 0 or not? Yes, definitely. How about it here? Can I write 0 as a fraction of two numbers?
Yeah.
Like what? 0 divided by 1. Right? So I get 0 on both sides. Here's me, Virgil, saying I can do this A by B, but I'm going to make B in the naturals. I'm going to say A can be any integers, but B is a natural number at least 1. Is that still correct? So the difference is in here, B cannot be 0, B cannot be 0, but the difference is this B can be any integer. This B can only be the positive integers. Would I get the same set? In other words, I don't need B to be -1 or -2. I can restrict B to just the positive set. Because when I do a fraction, if I want to have the minus sign, I can make A negative. And if I have negative by negative, I can make both of them positive and they're the same value. Equal means I get the same values. That's what it is. Right? Okay. How about the other question? Is Q enumerable? If somebody really wants to enumerate Q, so it wants to write down, is there an order for such thing? I want a yes or no answer.
Yeah.
Yes. Do you know how to enumerate it?
Yeah.
Okay, so that's an interesting question, kind of at the top of the honors level. How do you enumerate Q? What's the right order to get to all the rational numbers? We'll get to that later, but you can start thinking about it. Obviously, enumerating N or Z or so on and so forth is very easy with dot, 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 but how do you enumerate Q? How about I? Who's I? I don't know how to write R as enumeration, and I don't know how to write R as a property either. Do you? I only know the English definition. Set of real numbers. Of course, this mathematically means nothing because I just moved from a symbol to the word real, which is not defined. What are the real numbers? Can anybody tell me either enumeration or a property? By the way, this is called the set builder notation. Builder notation. It's just a name, of course. It defines a set as a property instead of enumerating it. So, back to my question. Can I define R either as an enumeration or as a set builder? Yes.
Why wouldn't it say that you could define it as the union of the rationals and the irrationals?
So I define this as what? Q?
Q union and then the irrational numbers.
Union I don't know yet.
Okay.
But let's say, yeah, let's say what? Irrationals you say?
Yeah.
So that's like IQ maybe, something like that.
IQ.
What he means by union is any x with a property that it's either in Q or in this IQ. That's what he means by union. It's in one of these two. I don't have a problem with the union. I have a problem with the set IQ. I don't know who that is. Do you? What is irrational? Like any real number, it's either rational or irrational. But I know what rational is right here. But I don't know what irrational is. So that's rational. Irrational. Anybody knows the definition of R? Even common sense. It doesn't have to be very formal. Some definition that gives me the real numbers.
Kind of a guess here, but like if you define it as a number that could be expressed as being between two integers.
Any number between two integers?
Yeah, if it's a number that can be between two integers, then it's a real number.
I'm not, yeah, I mean, informally that's true, right? Every real number is between two integers. But the between space is not really well defined. Rationals could say the same, right? I can define the rational the same way. Irrationals are numbers between two integers. Yet, clearly, we know that there are some real numbers which are not rational. This comment here implies irrational numbers, means there are some numbers which are not rational. Anybody knows an example of that? A number that's real but not rational. Yes?
Root 2.
Root 2. So square root of 2, apparently, it's not a rational number. That is, square root of 2 is in the set IQ, irrational numbers. What he means is that square root of 2 cannot be expressed as a fraction of integers. There's no fraction of integers that will give the square root of 2. Of course, that requires a proof. Do you know the proof? So why is it that no integers, when you divide one to another, can give you the square root of 2? That's a proof. But we need to worry about that at some point. So yes, what's another example of a irrational number? Yes?
Pi.
Pi, right? That's the ratio between the circumference of a circle divided by the diameter, right? So this is a circumference of a circle divided by the diameter of a circle. That's 2 pi r, and the diameter is 2r. So that ratio is a constant for all circles, and the number is pi, and this pi is not rational. There are no fraction a divided by b who gives a ration. Yet we still did not define all the real numbers. The fact that we found two of them, square root of 2 and pi, doesn't mean we know the definition. We know they're between integers, but so are the rationals, so how do we make sense? Let me ask an easier question. Can we enumerate that? Is there a way to kind of establish an order that enumerates all the real numbers? He says no.
Could you use like interval notation with mine?
Interval notation?
Yeah, just like from infinity to infinity.
Right, but that's the same as saying between integers. I don't know what do you mean by minus infinity to infinity, because integers are also from minus infinity to infinity, right? It's just more spaced out. So I know this is probably something you haven't seen. It's worth thinking about it. What R is, it has to do with the previous lecture. It's the limits. So what R is the set of all possible limits of sequences. All A's with the property there is a sequence of rational numbers, A1, A2, A3, so on and so forth. These are all rational numbers. And the limit of that sequence is A. So if you consider all the infinite sequences of rational numbers, and you take all their limits in the sense we defined last time, every limit is a real number, and every real number is a limit. That goes kind of beyond what we need to do for the discrete math. But you should know this. What are the real numbers? They are the limits of sequences of rational numbers. And it's quite easy to see why. Take the square root of 2. How much is it in decimal with approximations?
1.4.
It's about 1.4142, something like that, right? What is the sequence that will converge to this number? Rational numbers. 1, 1.4, 1.41, 1.414, 1.4142, so on and so forth. This is a sequence that if you build it careful, will have the limit that value. So rational numbers are dense enough that you can find numbers going to every single real number close enough to them. All right. So we have a set builder notation. Let's take some examples that are more down to earth. S is a set, all the integers, absolute value less than 5. What is this? If I enumerate it, -4, -3, right? -3, -1, 0, 1, 2, 3. Size of S, written like that, it's how many, the number of elements. So in this case, it's how many elements are in there. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 elements. How about for n? How many elements are in n? The size of n is what? Infinity, right? How about the size of z? Infinity. How about the size of q? Infinity. How about the size of r? Also infinity, right? Are those infinities the same infinity? Like, in other words, is there a way to say, okay, two sets are infinite? How can we tell some have more elements than the other, even though they both are infinite? Does that even make sense to say two infinite sets? They have infinite amount of numbers in there, but one is bigger than the other. That's something we're going to need to answer later.
Because one of the infinite sets is a subset of the other one?
Yeah, but, so that's true, right? So what he's saying, n is a subset of z, is that true? All the n is in z, which is a subset of q, right? Which is a subset of r. All the natural numbers are integers, all integers are rational, all rationals are reals. So either those infinities are the same, or these guys on the right has to have more elements than the one on the left, right? If this is a subset of that, this might have more elements than n. In fact, it does, right? Z has elements that are not in n, yet we call all this infinity. My question is again, how do we know it's the same infinity or it's a different infinity? Yes?
Maybe we could say that the spacing in between values of the sets,
Like the difference between them in n and z will be the same because it's one space?
maybe
So-
an minus 1, or a to the n minus 1 minus a to the n, or the other way around.
I think it means
bigger than-
these guys have the same spacing between elements. What's the spacing? 1. So I think it implies they're the same infinity because they space at distance 1. How about this one? Has the same spacing as them? Or is more dense? Maybe this one has more elements. How about this one? Is this one more dense than Q or kind of the same and dense as Q? More dense. So maybe R has more elements. We need a way to define what do we mean by the same number when the sets are infinity. I can tell you for now that those three are the same infinity. And this one is we'll get to that later. But for now, let's just say they are the same infinity because there is a way to enumerate them. Right? Somebody pointed in the back that there is a way to enumerate Q. That's an exercise. How do I enumerate Q? once I enumerate them, N, Z, and Q are enumerable. This is not enumerable. So it cannot be enumerated. That's why they different kind of infinities. This is the enumerable infinity that I can just one by one build it, all of it. And this is not possible to enumerate. For finite sets, right, means the size of a set is a natural number. Is there a set that has empty set, like no elements? It has a symbol like this, right? And we say the size of that set is 0. In fact, there's only one set, empty set, right? There's not multiple empty sets, it's only one, the set that has nothing in it. Right? Here's some illustration. I define a set which I'm going to call universe. 1, 2, 3, 4, say all the way to 10. And then I define A, the evens, which would be 2, 4, 6, 8, and 10. That's an enumeration. I can write this as a property. I want all the value in my universe with the property that x is even. Or if I want to write the predicate, I say even of x. And B, the set of odds. Of course, that's 1, 3, 5, 7, 9, which if I define in set builder notation is all the not even. Because those are the ones that I can also define this in terms of divisibility. I could say here's all the x's with the property that x mod 2 is 0, right? That's what even means. And this is all the elements in U with the property that x mod 2 is 1. That's what odd means. So now how do I illustrate this as a figure? I say here's my universe, and here is 1, 3, 2, 4, 5, 6, 8, 10, 7, and 9. Two, 4. That's the A set. 1, 3, 5, 7, 9. That's the odd set. So these have no intersection. A and B at this joint. No common element. If they're disjoint, also together they form the universe, right? A union B is all the x's that are either in A or in B. It's called union. Is that the universe? So they disjoint, and if you put back all this, you get back the universe. That means they form a partition. AB, a partition. Partition of set U. They disjoint and together compound U. So I'm going to have a set C in there. Let's say set C is smaller or equal than 5. It's all the elements in the set U with a property f being smaller than 5 or equal, so that is 1, 2, 3, 4, and 5. So where is that? 1, 2, 3, 4, 5. This one, this is A, this is B, and this dotted one is C. That has 1, 3, 2, 4, and 5. So now, who's A intersect C? Let's call intersection. And means what? All the elements that are in both sets. You can also read it as common elements or in both sets. So which one is that?
2 and 4.
Hmm? What elements are in both sets? Meaning in A and C. A is the one of the evens, C is the ones that smaller or equal to 5. So what? 2 and 4. I can translate this directly into a property statement with set builder. I say X in A means X mod 2 is 0, that's X in A, and X smaller than 5. Yes?
Is there a reason for any
I'm not. So I should write the same X everywhere, but sometimes I write it wrong, sometimes I write it. You should not do that. What people do when you study linear algebra, X, it's a scalar, and X like this is a vector. But I sometimes speed up and you can have all X's with a dash. How about B intersect C? So I mean the odds that are less or equal to 5. Mod 2 is 1 and X is smaller than 5. So which set is that? 1, 3, 5. So that's 1, 3, 5. If you look at visually who C is the 1, 2, 3, 4, 5, and if you look at who B is set in here, then 1, 3, 5 are the elements involved. The last thing we need to do is a subset. Subset, we say here's a subset D included in, say, B, if, as a definition, if every X in D also belongs to B. So that's the notation. Subset, it means everyone in here, it's also in here. For example, N is a subset of Z, because every natural number is an integer. But the other way is not true. Z is not a subset of N, because there are elements in Z which are not natural numbers. Because there is, say, X equal minus 1, which is in Z, but minus 1 is not a natural number. So I know it's I draw it there, but I wanna draw a little bit more like kind of a nice visual. Here's a set A, here's another set B. This is the intersection. And this is the union. The definitions are right here. Union means everything that's in A or B. Intersection means elements that in both of them, A and B. Right? And we also have two more definitions here. The difference A minus B. Sometimes people call this a straight minus. Some books makes a difference, like the minus is not the number minus. Sometimes it's a diagonal minus. They mean the same thing. Which ones are those? Those are the x's in A that are not in B. So that's in here. And in here, we have B minus A. So B minus A X is in B that are not in A. So what happens if I do, for example, in this example here, say I do A minus C. So A again was who? 2, 4, 6, 8, 10. Minus who was C? 1, 2, 3, 4, 5. So which elements are in A but not in C? 6, 8, 10. How about C minus B? That is 1, 2, 3, 4, 5. Minus B was 1, 3, 5, 7, 9. Is that true? So what elements are in there? Okay. How about the other way, B minus C? 1, 3, 5, 7, 9 minus 1, 2, 3, 4, 5. Who is this? So clearly this difference is not commutative. What's in B and not in C is different than what's in C and not in B. And you can see that by the visual. One difference is this side and the other difference is this side. That's not the same elements. In fact, what can I tell about those two sets? Can I have any common elements in here? In A but not in B, that's one set. B but not in A, that's the other set. Those have to be different elements, right? Because those ones are in B, not in A. How can they be in A? So sometimes there's another name for these. I don't think you're going to need this, but just in case. That is all the x's that are in A but not in B. That's A minus B. Union all the x's that are in B but not in A. That's B minus A. So that's this part, the symmetric difference. This and this union, excluding the intersection. It's like a XOR. Remember XOR? XOR was when only one of them is true, not both. So in here, these are elements that are only in A but not in B. These are only elements that are in B but not in A. Symmetric difference is like XOR, where it's true when it's either that one but not the other one. So it excludes the intersection, which is both of them. So I'm going to make a statement here that this symmetric difference A minus B union with B minus A is the same as the whole union minus the intersection. Is that true? I can look at this visual and say, if you want this and this together, it's the same as taking the whole thing, but excluding the common part. How do you prove such a thing? That's a theorem, right? How do we prove two sets are equal? When somebody says, this set is the same as that set, what does that mean? Yes?
They both contain the exact same element.
So the proof has to have two parts. One part will be any element that's in the left side, A minus B union B minus A, implies what? That element has to be on the other side. So that's the fact that saying this is a subset of that. Every element in here must be an element in here. Hands up who's with me. If I want to prove two sets are the same, I have to prove two things. Any element in here is in here. And the other one will have to be the other way. Every x in the right side, A union B, a minus A intersect B, implies x is in A minus B union B minus A. So I want to do the proof. That's an exercise. I just say that we need two different proofs here. But let's have an intuition without writing on the board. What's the intuition? If I take an element from here, how do I prove it's in there? In fact, what do I have to prove? How do I prove a set is in a difference? So I pick an element from this side, A minus B, B minus A, with the union. And I want to show that that element must be in here. How do I prove it's in here? This is a difference of sets. What do I have to show? Somebody else. Yes.
That it's in the first set and not in the second set.
It's in this and it's not
in this.
Right. So now that I know x is in here, how do I show it's in the union? Right? I have to make this implication. I take any element of A minus B union B minus A. That is element from here or from here. And I say, now I need to show it's in the union. Yes?
You can show that A minus B is a subset of A, and B minus A is a subset of B.
Very good. A minus B, it's always a subset of A, right? Is that true? Can we write that as a theorem? I don't want to interrupt you, although I did. But please keep your thought for a second. She's saying A minus B is a subset of A. If you take some elements from a set, whoever B is doesn't matter. If I take some elements out, I obtain a subset of that set. Right? So she's saying A minus B is a subset of A. What else?
B minus A is a subset of B. So the union of those two subsets is in the union of those two sets.
That's another theorem. If X is a subset of A and Y is a subset of B, then X union Y is a subset of A union B. That's what you're saying? Okay? So this whole thing is a subset of this. Therefore, any element in here has to be in here. Very good. That proves only one part, right? I still need Y is not in here. How do I do that? Why is it that an element in here, I already proved it's in the left side, that's good, but now I need to prove it's not on the right side. How do I do that? The easiest way to do that argument. How many people follow her argument for the first part? Taking an element from here means it's got to be in the union. Why is that? This first set is a subset of A. This B minus A is a subset of B. Then the union of them is a subset of that union. That's this theorem in here. Therefore, any element in there must be B. But now we need to prove it's not in the intersection. Because it's a minus, so it has to be in here, but not in the intersection. How do I do that? Yes?
You can say that the first part is subset of anything not in A.
The first part?
Sorry. On the left side, the first parentheses, they cannot be in B, and a union with something that cannot be in A. And so the intersection of those two cannot be.
So I think you have a theorem that says if X is a subset, it's is a subset of not A, and Y is a subset of not B. We have to get in a moment with what that is. Then the union X, I think that's the same as in here, is a subset of not A. That's the same X. Some elements are not in not A, the same elements are in not B, then they are in the intersection. But who's this not A? That's the complement of A, element not in A. This is not a well-defined mathematical statement. You can't just say not in A. It has to be with respect to a universe. So with respect to a universe U, that means A complement is simply U minus A. It's all the elements in the universe that are not in A. You're right, but I'm looking for a more interesting or elegant or simple mechanism. So his idea was correct, but I'm looking for a different thing. How do I prove that this in here is not in A intersect B? Remember where I am? I already proved that any X is in here. Now I need to prove that the same X's are not in here. Yes?
You could prove that when you subtract out the part of set A that's also in B, you take out the union of A and B.
Maybe you're right. I'm looking for a more direct proof. Somebody else, yes?
Can I use the picture to explain? Because,
Let's try.
basically, A minus B is like, that circle without the intersection, and B minus A has pretty much intersection. So basically, both of them don't have an intersection.
That's an intuition, valid. This one doesn't have intersection, this one doesn't have intersection. When you union them, you can't get the intersection because it's not here and not here. But how about we say that more rigorously? Yes.
A minus B is not in B.
What?
So A minus B is not in B.
A minus B
Is not a subsection of B.
I think you mean is disjoint with B.
Is this one with B? Okay. Yeah,
So not a subset means something else. So if you say this is not a subset of B, and I say what you want to say is A is disjoint with B. So this means disjoint. This one here says there are some elements in the left side that are not in the right side. Not being a subset could have common elements, but some of them are not. This one here says a different thing. What does it say? Those two sets have no common elements. Is that true? Everybody in B has been taken out from the left side, so it can't be common. I think that's what you mean. And the other one is?
B minus A is disjointed from A.
Okay, and therefore? It means put the glue in, you know, like I have the ingredients, but I need to cook them up now.
Therefore,
A minus B and B minus
And?
A. Union B minus A is not in.
Is disjoint to 2.
It's disjoint
With A and B, or A intersect.
This whole thing is disjoint to A intersect B, that's what you mean?
A union B.
I have a lot of question marks about this. Here's how I would try this proof, simple way, okay? Maybe you're right. I'm gonna prove by contradiction. Remember how those proofs go? If I want anything in here, what I want anything in here is not in A intersect B. So how do I prove this by contradiction? How do I start? Suppose it is in A intersect B. Right? So my theorem here is theorem. Any x that is in A minus B union B minus A means x is not in the intersection, right? That's what I'm trying to prove. Anything in the symmetric difference is not in the intersection. And that's what she was saying here intuitively. If it's in here or in here, it's avoiding the intersection. So here's a proof by contradiction. Assume, hypothetically, that x is in the intersection. Because the way it starts proves a contradiction is to say, let's assume the conclusion is false. And then if we obtain a contradiction, we're going to conclude that our assumption is wrong, the conclusion must be true. So now if x is in A intersect B, implies x is in B, correct? Which implies x cannot be in A minus B, right? If it's in the intersection, it must be in B. So when I do A minus B, since it's in here, in the one that's getting out, it's not in the set difference. But also x in A minus B implies x is in A, implies x cannot be in B minus A. So now I have this x is not in that set, x is not in that set. By definition is not in the union. Remember what union is? You have to be in one of the sets. But it's neither here nor here. By the union definition, x is not in this union B minus A. Because to be in union again, you have to be either in here or in here, which is not true. Therefore, that's a contradiction, right? Because that clearly disproves the premise. And what does it show? My assumption is wrong. It cannot be in the intersection. All right, we're going to play with this more. For now, I just want to introduce one more concept that I don't know when it's needed, maybe at a citation. And since we don't have enough time, we will just do the definition. There is something called the power set. So let's take this at A here. Let's just say 2, 4, 6. Power set called 2 to the A, just a name. It's no exponentiation, it's just a name. Is the set of all subsets of A, including the empty set. So who's all the subsets of A? Let's write it down. 2 to the A. That's the empty set. Is the set of just 2, the set of singletons. So this is a set for which its elements are also set. All the subsets of A. Doubletons, 2, 4, 2, 6, and 4, 6. Right? That's a set of 2, and all of it, 2, 4, 6, that's actually 8. So this is the power set. All the subsets put together, including the empty set, and also including itself. And I can do power sets for any set, right, whatsoever. Any set has subsets. I take all these subsets, and they form a power set. One last question. What's the size of the power set? How many subsets are there?
2 to the size of it.
2 to the size of it. And we'll prove that next time. Okay, remember quiz tomorrow and Thursday.
He does not need to go that hard.